Hi, my name is Trey Hayden, and I wanted to talk a little bit today about a situation that comes up in game dev where you may have one coordinate system that you would rather use for some sort of operation than another. The canonical example for this situation is something like an orbital camera, where you're mapping something, whether it's a mouse input or a game axis, and you want this to be converted into some sort of rotation or like a camera, which then needs to then translate its position back into a Cartesian space. So, when you see the sort of gizmos and axes in Unity, you get these blue, red, green, and these are in Cartesian space. And this is great for stuff that's forward, back, up, down, that kind of stuff. But it's not very good for stuff like rotations. And so I'm going to spend a little bit of time making a very simple orbital camera system. So if you've already made 15 of these in your life, I apologize. And then we're going to take that one step further from what I see tutorials normally do, which is just say, hey, congratulations, we've got an orbital camera, and that's the end of the day. And we're going to implement some sort of very basic spherical coordinate system from that, and then redo the camera system using the spherical coordinates. So here, I already have some dummy script here that isn't really doing anything. Preemptively, I'm just going to add the components here. When we go in here, we see just how simple this is, right? I have some sort of camera transform I would like to manipulate and something I would like to look at. There's nothing else really going on here. I'm not even going to use start. So typically with this kind of system, you have some sort of radius that I would like to keep track of, rotation speed. We'll start this off at 720 or something. Radius can start off at 5. And we have some angles we're going to play with. So let's say we want some sort of horizontal angle. This will start off at 0 and some sort of vertical angle. And we'll set this to 45 for now. It doesn't really matter what you pick here. And down here, I've got some input that I'm not currently doing anything with. So for Unity, your button number 1 on the mouse is considered right. So what we want to do is if the right mouse isn't down, just don't do anything. But only run this if we are holding right mouse down. So we do get the same kind of behavior that we get in the inspector, where right mouse is down, we can rotate the camera, and if it's not, it doesn't. So, all right, let's go ahead and implement the rotation component of the input, and then we'll deal with all of the actual camera manipulation after that. So mouse input equals mouse input times time to delta time times the rotation speed. So this will give me some sort of movement that I care about on the x and y axis of the mouse movement. We're going to increment our angles here. Let's equal mouse input x dot vertical angle type mouse input dot y, and that's more or less defined. Note that when we do this for the vertical angle, there might be a situation where it goes kind of too high and you get this awful looking asymptotic behavior over the characters. So let's go ahead and nip that right now. So public float vertical min, and we'll say this is -10 degrees, and then we'll do another one. We'll say that positive 70 is as high as we want to go. You don't have to do the plus sign here. Usually for me, if there's like a bound, a pair of bounds like this and one's negative, I like to put a positive just so that my brain kind of clicks, but this is obviously optional. So let's go ahead and clamp this then. Vertical angle equals f.clamp dot angle, vertical min, and this vertical max. If you're not a this enjoyer, you don't have to type these. I habitually type these so that I am confident I know where this is coming from. If nothing is in front of it, I assume it's either local or static in some very well understood context. So now we need some sort of function to take these two angles and our radius and convert some sort of local orbital camera position. So let's go ahead and do that now. So, yeah, it doesn't matter what it is. Private vector 3. Calculate orbital position. And we're going to take our radius, take our horizontal angle, we're going to take a vertical angle. So we need to take these two angles and get some sort of a pair of rotations, ideally. I see people do these with Euler angles, and if you want to do the Euler route, that's fine. Euler angles are one of those things that is like a really big red flag for me. I don't like using them if I can ever get away with it, so I'm going to do quaternions. So we're going to say horizontal rotation is quaternion at angle axis. We're going to pass in our horizontal angle. For the axis here, since this takes two values, for horizontal rotation, if you sort of stand up and put your arms out kind of in like a T pose, your spine is kind of what you rotate around when you're moving left or when you're rotating left to right. So we're going to do vector 3.up and vector 3.right for the vertical. And similarly for this, you just sort of imagine your right hand or your right arm is that kind of angle. That's sort of what you're hinging on. I guess your hips would also count as far as like looking up or down. So now that we have these, we can get our orbital rotation. And what we're going to do here is we're going to compound these. So horizontal rotation times vertical rotation. So in Unity, note that these are both quaternions. In Unity, there's an operator for quaternions where they kind of contextualize something else. And so in this case, the result here is a combination of both of these rotations. And we're going to use that to get some sort of orbital direction, or orbital position in this case. Orbital, I could type again. It's really hot here. I'm kind of sweating a little bit. Orbital position equals orbital rotation times vector 3.back. So the back, if this is confusing a little bit, let's just start with forward then, if you haven't seen this operation before. So in Unity, when you take a quaternion, one of the allowed operations you can do is multiplying it into a vector. So in this case, this is basically contextualizing the forward vector with respect to whatever this rotation ended up being. So the obvious one that comes to mind when you do this is transform.rotation times this. And if you were to do this, what you get is this .transform.forward. This is how this is computed. If you haven't seen it before, now you kind of had. This is a very convenient way of contextualizing direction vectors using a quaternion. So let's just go back there. And I want the backwards one because I'm interested in putting the camera sort of behind something. So that's what we're going to do here. So rotation. And I have my position, so that's what I'm going to return, orbital position. So let's get orbital position, calculate orbital position. Okay, arguments are mixed up, the radius, that's fine. So if it's going off screen a little bit like that, what I sometimes do with these like longer declarations is this kind of thing. And close it down there. If you want to pass in, oops, I didn't actually apply the radius. You don't need to pass stuff in like this, by the way. Like if you wanted to do the member version like this, you can do that just fine. This is another preference thing. I really don't like, mess that up too. I really don't enjoy having a bunch of stateful stuff in functions. If I can have pure functions, I will choose that 9 days out of 9. So I have our orbital position now. Now we need to get some sort of relative, what are we actually trying to look at? So look position, look target dot position, and then our final position that we actually are going to use, which is camera position. It's orbital position plus. So now what do we need to do with this is this .camera transform dot position equals camera position, and this .camera transform dot look at look position. The order here does matter. So look at is basically saying where in the world do I need to look to actually stare at this kind of thing? What rotation do I need from where I currently am to where I'm trying to look? Will allow me to sort of give the impression of looking at this target. And if you do look at and then assign position, you're using the wrong position to calculate the look vector. So be sure if you're doing look at, you've already established some sort of camera position to use. Just minor note there. Okay, and if we go back here, this should work. Yeah, there we go. Okay, so we hold the right mouse button down, excuse me. Can't look so far down, can't look so far up, and it seems to work. So this is great. And for the most part, this is kind of where the tutorials I saw stopped, right? We've made this kind of magical situation where we're converting from very planar mouse setup into some angle stuff. We're doing some magic, and then we get some sort of position back. And so what I'd like to, mention here is that this is essentially a spherical coordinate system that we've derived, where, I'm not taking anything, I'm not going into spherical, I'm sort of starting there with the sort of incrementing of the pair of angles. Then I'm generating a Cartesian coordinate based on those values. So what we're going to do now is just take one step further. And let's just derive our own spherical coordinate system using the information that we've already gleaned. And if you've taken a whole bunch of math, maybe you were a little bit familiar with this. And if you haven't, maybe you thought it was a little bit too spooky. But there's nothing crazy going on here. In fact, I'm literally just going to copy and paste some of these values up here. So we don't need rotation speed anymore. Note that everything's red because this is a struct. We should not have field initializers. Okay. And that's that. So I'm not even going to use a, I guess we could still make a constructor. Radius, float, horizontal angle, float, vertical angle. I don't think this example will use a constructor like this, but we might as well have it. In case you end up doing something like this in the future, you don't have to type then. Okay, so the only complicated math here that we haven't seen before is this ability to take a Cartesian coordinate. I'm going to call this static function from Cartesian. Get vector 3, and take a relative position. Okay, so we're going to make a chord. Give it a short name because we're going to type it a few times in a row. Okay, the simplest one here, because again, we need to assign 3 values here. We need to determine a radius, a horizontal angle, and a vertical angle based on a relative position that was assigned to us from the Cartesian space. The radius is the simplest one, relative to this position dot magnitude, just how far away am I from the origin, or relative origin at least. And then these other two are a little different, but if they might look familiar if you remember a whole bunch of your trig or something. So the horizontal angle here is going to be the arctangent. We're going to do tan 2 so that we don't get asymptotic stuff. And this is going to be the relative to position at x and relative to position at z. Not too bad. And then the last one is the goofy one. And this is going to be arc cosine. And it's going to be of the relative chord at y divided by the radius. Really having a good time typing today. And this should be it. We're going to make one more adjustment here, though. So note that for here, these functions dump out things in terms of radians, which is our first issue. Our second issue here is that, this is the sort of classical definition of where arctan would kind of dump us and where arc cosine would dump us. So instead of doing this, what I'm going to do is say minus 90f in terms of degrees, but I'm also going to make sure that these are actually in degrees themselves. Okay, and now that we have that, we're basically done. We need to do one more thing though. Obviously, we have a way of getting into spherical space from Cartesian space, so it would be great if we could actually get back into Cartesian space. Let's do that now. Click vector v2 Cartesian. Okay, now we already have a function that basically does what we want, so let's just start from there. And we're going to do this a little bit differently. There are 2 things to note here that will goof you up if you try to just drop this in verbatim. The first is this use of back. So initially we were looking at this from opposite direction, so like outside kind of in. And what we're going to do now is do the opposite. So we're basically looking from inside out. So this is going to be forward. And so by default, that should be fine. But the other caveat here is this use of vertical angle. And so you already offset this by -90 so that we get some sort of -45 to, or -90 to +90 range that we're more comfortable with, rather than just a 0 to 180, which might not be obvious. But the issue here is that the vertical angle that we played with before, positive meant looking down. And so if we just drop this in already, like it will clamp the opposite, so it'll allow 20 degrees north and sort of -70 south as the limit. And so for the sake of this, just so everything kind of works, what I'm going to do is chord vertical angle times equals -1. You don't need to do this. The math works out the same if you don't. You would just have to flip your clamping stuff around. But for the sake of like, you know, you have to pick some sort of scale for how you want to interpret the vertical angle with any sort of coordinate system you're going to do. And for mine, since this is my video, I'm going to use this. You are welcome to do whatever you want. Down here, I'm going to do vertical angle, minus. I'm going to swap this in. So this should work now. So what I want to do next is take this Spherical camera controller, and I want to make basically the exact same camera controller, but instead of doing this sort of explicit angle stuff and that kind of thing, I wanted to use the spherical coordinates. And so take this up here, get my look position, camera position down there is fine. And we're gonna gut this for now. I want to keep this vertical angle here because we're going to use it in a second. But for here, what I want to do is get some sort of camera position relative. Camera transformed up position minus the, where did my mouse go? Look position. Okay. Now with that, where's my look target? Up here. Oh, I didn't rename this. Spherical camera controller. Okay. Okay, there we go. Okay, now my spherical chord from Cartesian, camera position relative. Because again, we're passing in a relative position around something, it doesn't matter what. And spherical chord, horizontal angle, vertical angle. Let's also set the radius here because we can do that. This is all very convenient to do in this space. And now we're going to add a new function, clamp vertical. And I want this to use vertical min and vertical max. Your editor should probably have some way of doing this. Go back into here. A vertical angle, clamp. Let's do a vertical angle, vertical min, vertical max. Okay, make this public because I don't like seeing internal if I'm not using sort of library or something. Okay, this should be fine. All right, we now have our spherical chord properly defined. Now we need to get our orbital position back. So orbital position. It's going to be our spherical chord to Cartesian, this one we defined earlier. We already have a camera position, and we're not using this anymore. So if everything worked out correctly, should be able to go back to here. We still have our old component over here. Rather than swapping out, I'm just going to do this little trick. Note that everything is still preserved. And I'm going to hit play. And it works. How cool is that? So what is going on here is that we are taking the same camera setup we had before, where there is some sort of planar setup for input, whether it's mouse dragging along your mouse pad or a gamepad or something, mapping this into some sort of spherical space, manipulating the spherical space a little bit, and then returning some sort of Cartesian space. The point of why I wanted to cover this topic is that this is a pretty recurring theme for game dev, where it might be much more convenient to deal with a space that isn't Cartesian. What I'm showing on screen at the moment is from a project called Dive, and this attack in particular uses what's called a Fibonacci sphere, where the coordinate system is not Cartesian, and if it was Cartesian it'd be a huge pain in the butt. And it is in a cylindrical space, where it sort of tapers off to look spherical, but it's the XZ plane is still using basically a polar grid. And with that, the math ends up being much more convenient, everything ends up kind of playing out nicely. And so you don't need to do nearly as much math as you thought you had to do, everything just kind of falls into your lap. So whether it's that or something like volume mapping between normal space to logarithmic space for settings managing, there are a bunch of situations like this where, you know, if you just understand that there's another system that's much more convenient for you to use, map to that and then map back when you're done, it can save you a lot of really picky math that you'll otherwise just sort of found strewn about your code base. Especially for things like this, where if we go back to spherical chord, like this, like just stumbling upon this in a code base would be pretty annoying to find, especially to review. So personally, when I have something like this, I try to include like where I kind of got it, especially if it's math, so that whoever's reviewing it can see, okay, this is the link where it came from. This is why there's randomly an arc cosine in my project now. You might also want to include a comment for like this if you're flipping some axis around for negative 90 to plus 90 for above view. And then you're basically kind of done. Because this is the kind of thing where there's like, there aren't really a whole lot of ways to declaratively write this. So you might want to just inform the reader, like, why the hell is there just a -1 here? Anyway, that was all for today. Again, sorry if this is a bit repetitive if you've done a lot of these kind of orbital conversions before, but I hadn't seen it covered too much in Shoro space, and I wanted to just briefly talk about it for a little bit. So anyway, thank you for watching, and I hope you have a great weekend. All right, bye.